All right, so as promised, I am going to continue with our chapter 12. I am going to talk today about trig functions of general angles, and what that means is either in degrees or radians. We are going to be able to talk about what those values are, again, using our trig functions. Not only sine, cosine, and tangent, but again, we talked about their inverse or their reciprocal, their reciprocal functions, which is cosecant, secant, and cotangent. Again, cosecant is 1 over sine, secant is 1 over cosine, and cotangent is 1 over tangent. And we looked at that last week or two. The difference here is now what we're going to talk about is some point that we're going to put on our graph, and it's going to be an ordered pair. And the nice thing about an ordered pair is it already tells you the horizontal distance x and the vertical distance y. And this time we're not going to be talking about the unit circle, so to speak. We're going to be talking about any value that we use for x or y. We're also capable of figuring out what that specific radius is. So before, when we were talking about the unit circle, we always knew that r was 1. In this case now, when we change our horizontal and vertical, the radius won't always be 1. But the nice part is we have these right triangles here where we're able to incorporate the Pythagorean theorem. But then every time with our right triangle, we do have the capability then of, regardless of what that angle is, so it doesn't even have to be one of our special rights, we do have the capability of using our trig functions to use, and remember, if our angle again is down here, opposite over hypotenuse, so the vertical distance over the radius, adjacent, our horizontal distance over the radius, so adjacent over hypotenuse, and then our tangent, which is opposite vertical distance over adjacent, our horizontal distance. So notice how opposite over hypotenuse, adjacent over hypotenuse, opposite over adjacent, those have all changed now to these x, y coordinates and r, the radius. So mean the same thing, are just designated now as something different because of us being on this coordinate plane situation. So that's what I have here. I just want you to remember that even though we're using y, x's, and r's, that it still follows our SOHCAHTOA rules. So again, when we're talking about these angles in standard position, that always is this counterclockwise rotation. So again, wherever that point is, we're going to be able to figure out all of our trig ratios according to this. So with that being said, of course, I am prepared with one of the examples from your textbook. If you ever take a look at the pages in your ConnectEd login, we do have this example problem. It's under the one that they give you, and we do have the terminal side of theta, meaning where does it stop, just like you see where point P stopped here, in standard position, again meaning it's opening counterclockwise, and we stop at point -6, 2. And we want to find the exact values for our 6 trig functions of theta. So again, that all has to deal with where are we ending. Well, we already know that even though we're back here at that -6, that distance is 6 in our Pythagorean theorem. The vertical distance is 2. So what I have to do is I have to figure out our radius. So what I did here was I already used the Pythagorean theorem to figure out that our radius is going to be 2 radical 10, because the square root of 40 would be 4 times 10, or 2 radical 10. So don't forget, though, that we're back here in this second quadrant. So x is negative. Notice the -6 is still there, and it's down here. Y was 2, And now we know our radius is 2 radical 10. So I'm going to follow those formulas that we did say are opposite over hypotenuse, adjacent over hypotenuse, and opposite over adjacent. But now it's y over r, x over r, y over x, and then all of the reciprocal functions. So r over y, r over x, and x over y. So once we know these three, we just have to flip them here. So let's just use these three, and now we have 2 over 2 radical 10, which we know we can't keep a radical in the denominator. So I am going to first reduce the 2's, so it's 1 over radical 10. And we know that the radical gets yanked to the top and just the radicand on the bottom. So our sine theta is radical 10 over 10. Cosine, well, again, don't forget that's a negative 6 over 2 radical 10. Again, I'm going to simplify it first to negative 3 over radical 10. And that, again, means that I'm going to take the radical to the numerator because we're multiplying by radical 10 over radical 10. And it leaves us just with 10 on the bottom. Tangent is opposite y over adjacent x. So we have that 2 over negative 6, which reduces this to negative 1/3. So I'm going to use all of these first fractions to help me do the reciprocals here. So 2 radical 10 over 2 makes this just radical 10. 2 radical 10 over negative 6 makes this a negative radical 10 over 3. And negative 6 over 2 makes this a negative 3. So every one of these final outcomes are the trig functions, are trig ratios for theta. Okay, those are the exact values. We didn't have to worry about decimal rounded answers. All right. So now what we're going to look at is what happens if our angles don't fall someplace inside one of the 4 quadrants. What happens if they actually fall on one of our axes? So what happens if theta is 0 degrees or 0 radians? It also could be that it came all the way back around and was 360 degrees or 2 pi radians. We have our 90 degree, 180, and 270 that all kind of fall into those same categories where they line up on one of our axes. Those are called quadrantal angles. Kind of sounds silly, but where they actually fall on one of our axes. Nothing's going to be any different except that it's a little bit easier in that really you don't have to worry about your Pythagorean theorem. Because you do know that if you do put negative 2 squared plus 0 squared and take the square root, you're coming right back with 2. So that radius isn't going to change just because it's now located someplace else. So we're already labeled here. So if we're going to do our 6 trig functions again, so we have our sine theta, cosine theta. That one isn't working. I did that yesterday too. Sine theta, cosine theta, tangent theta, and then we have all of the reciprocals, cosecant theta, secant theta, and cotangent theta. So in each case, if you don't already have them memorized, you can write them out as you go. But we do have, again, that sine is y over r. We have x over r. We have y over x, and then all of the reciprocals, r over y, r over x, and x over y. And now I'm just going to use these values to plug them in. So for sine theta, where our terminal side falls on -2, 0, y is 0, 2, so sine theta is 0. -2 over 2 is -1. 0 over -2 is 0. We're going to deal with now our reciprocal functions. So 2 over 0 is undefined, can't happen. Falls out of what the domain is allowed to be, because can't have 0 in the denominator. We have 2 over -2, which is -1. And we have -2 over 0, which again is undefined. And what you're going to find is this pattern. I don't want to necessarily call it a pattern, but these zeros and ones and undefined come up with your quadrantal angles. So nothing different, just the fact that that's what they are referred to as, and at least it makes it a little bit faster when you're dealing with your Pythagorean theorem. These guys right here, for some reason, I remember a lot from when I was in school doing this, so I'm not sure if we just practiced it a lot or if that was something that's just going to keep coming back. So make sure that you take a look at those. All right, so of course we're going to have values that aren't going to constantly be, again, values that are 30 degrees or 60 degrees. We are going to have angle measures that are going to reach into other quadrants, so they're going to be obtuse angles. They're going to be greater than 180 degrees. So what we're looking at is how do we work out something, especially in our calculators, where our calculator may not, depending upon which one you have, may not work with values that are in the quadrants that show up as a syntax error. So what we have to worry about is what are called reference angles. Now, anything that falls into our first quadrant, the reference angle, this theta prime, it's not really called theta prime, but it's our reference angle, so theta with that little dash, they're going to be the same. You don't need a reference angle for this first quadrant, but the minute we start entering all these other quadrants, your reference angle is going to be the one closest to the x-axis. So because your reference angle here is smaller than 180, we would just figure out what 180 minus theta is, and that would be your reference angle, or pi minus the theta, depending upon if we're in radian measure. If we go greater than 180 degrees, we are going to look at this guy down here. Well, now our angle is greater than 180 degrees. So we're going to take our theta and we're going to subtract 180 to figure out what our measure is. So just always trying to create these positive values for your reference angle. So again, the reference angle is always the one closest to the x-axis. It's going to be the one that's smaller than the 90 degrees or 180 degrees that we're looking at. And then if we're almost all the way around and we're stuck there in that fourth quadrant, what you're looking at is, again, the 360 because we're real close to that x-axis there, minus our theta, or the 2 pi minus our measure, depending upon if it's in degrees or radians. So the first thing is I just did two very quick, because they even asked it in the book, figure out what the reference angle is. So I didn't draw the first one because I didn't need to. I could see that 210 was definitely bigger than 180 degrees, so I knew to keep that measure a positive reference angle. I'm going to take that 210 minus 180, and I end up with theta equals 30 degrees. So our reference angle, theta prime, is 30 degrees. So if I was to do any calculating at this point, I would use my 30-degree angle with a little bit of other information we're going to look at next to figure out what we're talking about with 210. Now, what I did have to do is I kind of approach this like you. Like, I don't know where negative 5 pi over 4 is. I don't have those radian measures memorized. So I want you to take a look what I did down here in my brain bubble. And I'll zoom in real quick. I wanted to look at it like, how do I figure out where that goes? So I changed from radian measure back to degrees so that I could figure out what that measure is. And I found that it was negative 225. So notice that I went clockwise now until I hit 225, that negative 225. Well, I don't deal with negatives, so what we had to do was we had to figure out what that positive coterminal angle was. So you can see here that I'm talking about we need our coterminal angle. So if the whole thing's going to add up to 360 degrees, if I took that 360, 2 pi, and I subtracted the negative 5 pi over 4, what I find out is the leftover is 3 pi over 4. And I'm hoping what you can see is if we did do that, that's an 8 pi over 4. So all the way around is 2 pi. So coterminal angles end in the same spot. That's where that 360 degree idea comes from, or that 2 pi. So in order for me to figure out what this reference angle is, I need to figure out what this difference is to the x-axis. Well, if it's 3 pi over 4 to get to here, what's left is pi over 4. So if I was to do any work, again, we're going to take a look at that. I need to know what that reference angle is in order for me to continue with my efforts. So that's why I wanted to kind of show you how we can calculate the reference angle. Some of them were real easy. You're going to be able to do them in your head. Others of them, you may have to kind of think through it a little bit until you get really good with memorizing radian measure, just like we're really good at memorizing degrees. So that's why I kind of showed you how I knew where to go by changing it back to degrees, just so that I can kind of get a visual, figure out what that positive measure would have been, that coterminal measure, and then we can calculate what that reference angle is. So how is this all going to work together? Well, one of the things that we need to do is not only figure out what our reference angle is, again, that's the symbol for reference angle, but when we evaluate using that reference angle, we have to remember that in all of these different quadrants, our sine, cosine, tangent functions are going to have different values, positives, negatives. Again, in the first quadrant, we know everything's going to be positive. But what we also saw in this first example, sometimes they come out to be negative because they're in different quadrants. So even if we had something that ended up down here, a negative over a negative would end up being positive depending upon how its relationship is. For instance, notice the vertical and horizontal with tangent and cotangent. would, if they were both negative, a negative divided by a negative would be positive. So what we started this with is how this was created. So what we're looking at is how does all of this work out? And I am going to look at something very quickly because for some reason I feel as if I put something wrong, and I don't want to continue if that's wrong. Because notice I have all three negative here. I can say that I don't believe that's correct because I just said negative over a negative. And notice how that's positive and that's positive. I need to look at that a little bit. So all I'm doing is right now going to your ConnectEd book just to figure out if I copied that incorrectly. And I feel as if late last night I did. Although I'm running here, so of course it's going to go real slow. So as I look that up, I am looking at the fact that we first need to evaluate for our reference angle. Then what we're going to do is we then determine the sine. So every time I work any of these out, we're going to figure out what our reference angle is. We're going to work out our trig function, opposite over hypotenuse, adjacent over hypotenuse, opposite over adjacent. And then we're going to figure out where is it positive or negative. So again, we can, oh my goodness, stop moving. We can look at our chart. So a lot of times I said, keep your cheat sheets, your notes close until you have them memorized. I was right. See, trust, negative divided by a negative is positive. Just wanted to make sure. So I have find the exact value for our cosine of 240. Well, if it's saying exact value, then what we're looking at is that our reference angle is going to have to be one of our special rights. So keep that in mind. Anything that isn't a special right, 30, 60, 90, 45, 45, 90, you're not going to be able to get an exact value. So even if we did use the steps, find the reference angle, find the value, and then determine the sine, if it's not going to have a reference angle that's 30, 60, 90, or 45, they're not going to ask for exact value. Okay, you're going to end up having to give a decimal. So the first thing that we did, notice first, is we figured out what that reference angle is. So if we're at 240 and we want to be by our x-axis, we're going to subtract that 180. We end up with a reference angle of 60 degrees. So now I'm going to, instead of cosine of 240, I'm going to evaluate cosine of 60. And that ends up being 1/2. Now, I could have gone to my calculator and plugged in cosine 60. And we would have found that it said 0.5, so 1/2. However, what we also know is all of that information that we did with our unit circle would have told us that cosine of 60 is 1/2 because we would have done our adjacent over hypotenuse work, but we also should have that memorized according to our special rights. Okay, that 1 to radical 3 to 2 relationship. So we do have this. But the third step that I have to remember is I have to figure out what the sine is. So I go back up to my chart and I think about if I'm in quadrant 3, cosine's got to be negative because our horizontal or vertical, remember that x over y, x over r, y over r formula tells me that it's going to be negative in quadrant 3. So the thing that I have to keep in mind is that it's going to be negative. So when I write my final answer of the cosine of 240, it's going to be a negative 1/2. So first step, find your reference angle. Second step, evaluate it for that reference angle. And the third step is make sure that you determine where it's positive or negative, and then write your final answer. All right, so here again is the issue that we have our radian measure. So I needed to make sure I figured out where that fell. So I did look at 5 pi over 6. I did multiply by 180 over pi, or I could have looked at my unit circle and had that in front of me and know that our 150 degrees is 5 pi over 6. But what I am working with now is this reference angle, and that would be our 180, so pi minus 5 pi over 6 leaves us with just pi over 6. Pi over 6 obviously is going to be 30 degrees. So 30 degrees on my unit circle, we could tell that it was, or writing out your special rights. And again, if we're not sure, just draw your special rights. No matter where you put your 30 degrees, remember, opposite the 30 is 1 of something, opposite your 60 is radical 3 times something, and opposite the 90 is 2 times something. So it's this 1a, a radical 3, 2a. But again, if we don't know what that common factor is, it will all reduce to a 1 to radical 3 to 2 relationship. And when it does, if I'm looking at tangent of 30, tangent is opposite over adjacent, 1 over radical 3. And when we simplify, that's radical 3 over 3. Again, we talked last time about memorizing our special right fractions. So if we have that memorized, I know that tangent of 5 pi over 6, which has a reference angle of pi over 6, so tangent of pi over 6 is going to be radical 3 over 3. But tangent is negative in quadrant 2. Notice where our terminal side fell. So when I write my final answer, it has to be negative radical 3 over 3. Step 1, figure out what your reference angle is. Step 2, evaluate for the reference angle. And again, it's exact value, so we knew it was going to be a 30, 60, or 45 degree angle. The third step, where is it positive or negative? And then write your answer. And again, if you don't have that memorized, draw out your special rights, calculate it, and then write the answer down. So here's an example of, again, your textbook gave a similar example with a really nice picture of what appears to be something like Skyhawk from Cedar Point. They gave a different scenario where the swing was much taller. It was at 97 feet off the ground instead of a mere 88 feet, right? And it says the swing arms of an amusement park ride are 72 feet long. So again, depending upon how long it is when you sit in those crazy seats on Skyhawk, which I will never do. I don't care what the physics behind it tells me is okay. That's freaking terrifying. So we have a 72-foot long arm that the swing's going to have you on. The height of the axis, meaning how high is it from the ground, so from the ground to where our axis intersection is where the arms are going to connect, is 88 feet. And the angle of rotation in standard position, all right, is that negative. So we know that it's going to have this pendulum swing, and it's going to go up to negative 195. So as it swings back and forth, it's going to reach up here. So we want to know what the total height of this ride is going to be when it hits that point. So that 88 feet up from the ground, and then that swing is going to carry us up just a little bit higher at y. So again, our vertical distance. Well, negative 195 we can't calculate. So what we have to figure out is what that coterminal angle is first. So that's that 360 plus the negative 195. And we find that our coterminal angle is 165. So that's the one we want to work with now, that counterclockwise direction. Again, we need to know the reference angle, which is closest to the x-axis. So our reference angle is actually 15 degrees. So we figured out our coterminal, then our reference angle. And now I can actually work out, because again, here's where that angle is. It's at that intersection. So if you're having trouble visualizing what that looks like, there's that vertical distance y. Here's that horizontal distance to the axis where it intersects. Here's the arm of our ride. And the arm of our ride, they already told us, was 72 feet. Well, if I know this guy in here, is 15 degrees, I can figure out what this side is, because that's the height I want to know, by doing opposite over hypotenuse, or y over r. Well, opposite over hypotenuse is sine. So I didn't just guess to use sine, it's the way our triangle is set up. Opposite hypotenuse here would have been adjacent if for some reason it wanted to know if it was going to reach out too far and hit a building, kind of like the swings in the back of the park, where you sincerely think you're going to be able to kick the top of the shed. So we have sine because y is our opposite side. The radius of how this arm is going to swing is our hypotenuse. So when we did this, that's why it's sine 15 is going to equal opposite over hypotenuse, or y over r, the vertical distance and the radius of this pendulum swing. Plug that in the calculator, sine 15. I created my proportion, cross-multiplied, and solved. So I just figured out that that vertical distance here is about 18.63 feet. Well, if I add that to the 88 that's already there, I figure out that the height of this ride is going to be about 106.6 feet. Obviously, when you look at some of the rides that we have at Cedar Point, the engineering behind them, this kind of stuff comes into play. So that's why I wanted to kind of give you that to look at. So that is where we're going to stop today. There, again, are the other examples from the book that they had already completed for you. I, of course, did the extra practice problems that were there. And what you will find is I will continue to add in order for us to finish the important parts of this chapter, even if we are done with school. I am going to add law of sines and law of cosines just to prep you for next year. And again, if you have any questions or any concerns, continue to email me. Check Google Classroom. And pretty much I'm here all summer, so if there's anything you need from me, please just continue to email. It's such a different situation, and I do not want you feeling as if you didn't get everything out of this you possibly could. Thankfully, all the videos are stored, so you can always go back and rewatch. With that, have a great day. Continue to finish up everything before tomorrow, and I will post our next video soon. Have a great day.